Ever since people could count, they have been curious about numbers. Some numbers more than others, particularly the primes. The only factors of a prime number are 1 and itself.
They act as the building blocks of all other integers, multiplying against each other to form composite numbers. Prime numbers can be exceedingly difficult to predict, but they are far from random. Their distribution is actually related to an entirely different area of math, and a stunning connection. It all started in the 1730s. Leonard Euler was researching something called the Zeta function. This function adds up all the reciprocals of a certain power. Euler was trying to find the sum of the reciprocals of squares, in the case s equals 2. Oddly enough, he found it to equal exactly pi squared over 6. What Euler did next with the function is astounding. In a beautiful proof, he showed that the zeta function is equivalent to the product of prime reciprocals. While this is an interesting relationship, the zeta function has not yet relinquished all of its secrets. At s equals 1 or less, the sum diverges, shooting off to infinity, so half the function is blocked off. Bernard Riemann was not satisfied with this. He decided to make another function, one that would be equivalent but also work for values less than 1. This is known as analytic continuation. What he did next was just as amazing. He allowed for complex numbers as inputs.
What Riemann realized was that there were not only trivial zeros, where the function outputs 0, and the negative even integers, trivial meaning easily explained, but the zeta function also contained zeros located on the line with real component 1/2. Riemann found that these zeros encoded information about the prime numbers. Zero corresponded to an oscillation, or harmonic, the imaginary part corresponding to their frequency. By adding the harmonic for each zero together, with a special function known as the logarithmic integral, he saw that the outputs of the function began to approach the distribution of primes.
But this would only be the case if each of the non-trivial zeros had real part 1/2. The real part of the zero corresponds to how quickly the harmonic would increase, and even a single zero with a different real component would grow much larger than the others and overpower them. This became known as Riemann's hypothesis.
While this may seem abstract, it highlights the importance of the primes, because there are a vast number of theories which rely on this hypothesis being true, some even in unrelated fields such as quantum mechanics. In math, surprising connection between ideas that seems to have nothing to do with each other. Often, huge discoveries that give us deeper understanding.